Okay, so today we're looking at a continuation of ionic compounds, but we're actually looking at a new type of ion that we haven't seen yet before called a polyatomic ion. Okay, so the term poly means more than one, and then of course atomic means atom. So a polyatomic ion is when you have an ion that is made up of more than one atom. So what it is it's a group or like a little cluster of non-metal atoms, and they are bonded together, but they carry an overall charge like an ion would. So when you're looking at this, I'll give you an example just so you can see kind of what I mean. So NO3 negative 1. So what this is a small little cluster of atoms, 1 nitrogen and 3 oxygens, that are bonded together, and all together they have a charge of negative 1. So whenever you're dealing with polyatomic ions, you have to think of them as being one unit. So this NO3, it's not nitrogen and oxygen. It's actually thought of as being one little cluster of atoms. So actually the name of this one is called nitrate. Every polyatomic has its own unique name. And actually we saw nitrate in the ecology unit when we talked about the nitrogen cycle. So how they are actually bonded together, like I mentioned, they are sharing electrons, and the bond type are covalent bonds, remember? And actually the next lesson after this, we're going to be reviewing that. But covalent bonds is where you have a sharing of electrons. But however, the reason why we're including this when we're talking about ionic compounds is because it is an ion. It does have an overall charge. So here are some common ones. So we have nitrate, which is NO3, hydroxide, which is OH, bicarbonate. Bicarbonate also goes by another name, hydrogen carbonate. Okay, which is HCO3, chlorate, chlorine, and oxygen, carbonate, CO3. Now the charge of the ion is always in the top right-hand corner, like it would with any other ion. So the charges that we can see for the ion charge is on our ion chart here. So this is just to show you how they come together. So nitrate, that's this guy here. So the nitrogen and 3 oxygens are a group together. So all together, notice there is the brackets and the charge. So when you're dealing with polyatomic ions, it's still an ion. The difference is it's not a single atom that's made this ion, it's a grouping of atoms. So you actually have a list on your periodic table of ions of polyatomic ions. You don't need to memorize them or anything like that. You have them available for you. So this is on the second page of your periodic table PDF that I've shared with you. Or on the back of your periodic table, but it's where you have all of the ion charges. This is up at the top. So here are some examples, right? So here is chromate, chloride. Well, chloride is not really polyatomic ion, but it's on there anyways. Borate, right? You don't have to memorize any of these. One thing I do want to point out, all of the ones that have hydrogen in it in the front of the name, so see how it says hydrogen carbonate, hydrogen oxalate, hydrogen sulfate, etc. These also go by another name, which we saw already actually. See how hydrogen carbonate can also be called bicarbonate. All of these that have hydrogen in front of the word for the polyatomic ion can also go with the prefix bi. So for example, if I said bisulfate, bisulfate is the same thing as saying hydrogen sulfate. So if you see that come up and you're like, oh, what the heck is bisulfate? It's because it's the same thing. It goes by different terms. So I'm giving you this terminology, but if you see this on a worksheet or anything like that, you should know, you're expected to know that that represents the hydrogen. Okay? So when we're dealing with polyatomic ions, we would do it in, like, we would behave it in the same way that we would regular ions. So when we're naming, we would still use the same name. When we're doing crisscross rule, we'll still do crisscross rule, but obviously it's a little bit of a twist because it's a different type of ion. So we're going to take a look at that. Okay, so polyatomic ions are composed of metals with polyatomic ions. Now, this is not always true because you can have a non-metal with a polyatomic ion. The reason why this is here is because if you take a look, so remember, metals become positively charged. If you look at this list of ions, there's not that many that are positively charged. Most of the polyatomic ions are negatively charged. So this will be true because your metal is positive, your polyatomic ion is negative. But you can have a polyatomic ion that is positive. So if the positive ion is there, that means that it's going to be matched up with a non-metal. The point is, no matter what, it doesn't matter what type of ionic compound it is, you need a positive to be matched up with a negative. Because remember, you need something that is losing electrons to go with something that is going to gain those electrons. So obviously, if we're dealing with positive polyatomic ions, it has to be matched up with something negative. So just keep that in mind. Okay, so writing the formulas is exactly the same as the crisscross rule we've been seeing before. But the main thing to remember is the polyatomic ion is considered to be one unit. Okay? When you're giving the names for polyatomic ion compounds, the name of the metal is always first, or think of it, the name of the positive ion is always written first, and then the name of the negative ion, which usually is the polyatomic. And the nice thing is, you don't have to change the name. The name of the polyatomic ion is literally whatever it is on this chart. Okay? So let's take a look. So we're going to do an example with sodium and sulfate. So sodium, and here's sulfate. Sodium is positive 1, sulfate is negative 2. So if this helps you to remember, put the brackets around the polyatomic ion. So this number 1 that's crisscrossing down, it will not crisscross where sulfur is. You have to remember that SO4 is a little bundle. So that positive 1 actually goes all the way to the outside of this number with oxygen. The 2 will come down beside sodium. So this will end up being Na2SO4. Okay, now the bracket there is just to help you. You do not write the bracket in unless, you're going to see in the next example, unless you have to write a number here. Because this is going to be the number 1, we don't put a bracket in. It's just Na2SO4. So this means 2 sodium and 1 sulfate. So when we name the compound, it's actually pretty straightforward. It's sodium sulfate. So just the name of the metal, the name of the polyatomic ion. Okay, we'll do another one. So here we have magnesium and sulfate. So magnesium plus 2, SO4 is negative 2. So the 2 would crisscross down beside magnesium. The 2 would crisscross on the outside of the SO4. So you have Mg2, SO4, 2. But just like with any other ionic compound, we always want to reduce if possible. So because this is a 2 and a 2, we're going to do MgSO4, like a 1 and a 1. Okay, so keep in mind, you cannot, let me be very clear. So the sulfur, like this, the subscripts that are in the polyatomic cannot be reduced. The only thing we're discussing being reduced are the charges after they're crisscrossed. Okay, so let me go back for a second. So all of these subscripts in these polyatomic ions, they have to stay as is. If you change a subscript, it changes what the polyatomic ion is, and that's not the point of this. So when we're talking about reducing down, we're referring to the subscripts of the charges that have been crisscrossed. Okay, so the name here is magnesium sulfate. Okay, so polyatomic ions are ionic. Ionic compounds are always simplified if we can. All right, so here we have tin 2. So remember, if you're dealing with one of the elements that has more than one option, you need the Roman numeral. So we have tin 2 and nitrate. So tin and nitrate. Tin is positive 2, nitrate is negative 1. So the 1 will crisscross down beside the tin, the 2 will crisscross down beside the nitrate. So this is going to be SnNO3 with the 2. So the brackets that I was showing you before have to stay if there is a number that is going to be on the outside of the bracket. Okay, so I'm going to explain to you why that is. So imagine for a second we did not use the bracket. So SnNO3 with the 2, right? So right now what this means, if you remember going back to counting atoms, that means that we have 1 tin, we have 2 nitrogen, and we have 6 oxygens, right? If you did not include the bracket, this is what it would look like. Okay, that means I have, when you're reading this, that means I have 1 tin, 1 nitrogen, and 32 oxygens. No. Okay, so you do not put the brackets if it's a 1, right? If you don't have a number there. But if you have to crisscross down a number that you have to write in, you must include the bracket. Okay, so the name of this compound would be tin 2 nitrate, right? We always include the Roman numeral if it's one of those elements that needs it. Okay, so here we have another one, copper 2 and carbonate. So we have Cu and CO3. This is positive 2 and negative 2. So the 2 and 2, right? So we have Cu2, CO3 with the 2. So this can be reduced to CuCO3. So the name of this, and we can't really fit it in there, let me extend, would be copper 2 carbonate. Okay, all right, so try these ones out. You'll need your periodic table to help you, so that way you can look up the polyatomic ions. So I want the chemical formula for each of these. So pause the video and give this a try. Okay, so here we go. Potassium hydroxide, KOH, no brackets. Calcium peroxide, CaO2. So peroxide is its own polyatomic ion. So this looks like it's a subscript that's been crisscrossed down, but actually it's not true. This was the original one. So we had, no, this should be negative 2, pardon me. So the 2 crisscrosses down beside the 2. So what we're actually looking at here is the reduced version. So it was Ca2O2, 2, but it's been reduced. Copper 1 nitrate, aluminum phosphate has been reduced, and barium iodate, you must keep the bracket there. Okay, we'll do the next part.